All right, so today we are going to take a look at rational functions, and there are components of this lesson that we've looked at on a couple of different occasions from different perspectives. And the first one that I'd like to draw your attention to is the idea of restricted values. So we've had functions like f of x equals negative 5 over x minus 2, and we've talked about the fact that that means there's a restricted value. So why would we say the restricted value is x equal to 2? Well, if I put a 2 in for x, what would happen to my denominator? It would be 0. Okay, and we can't divide by 0, so we would call that a restricted value. The question that we're going to explore today is, visually speaking, what's happening on the graph then at that point. At the x equals to 2 location, what's actually happening? All right, so as a way to start answering that question, the first thing we need to talk about is what it means for something to be a rational function. It's the title of the section. This right here actually is what we would call a rational function, but sort of what criteria have to be met for us to actually give it that label. So a rational function is a function of the form p of x over q of x, where p of x and q of x are polynomials. We've been working with polynomials quite a bit. So if you remember, polynomials don't have square roots. They have exponents that are positive or maybe 0. Like they don't have a constant there. So we've got values on the top and the bottom of a function, all right, of a fraction even, if you will, that are each polynomials. So on the previous slide, we had this equation written out. And negative 5 is a polynomial. Constants are polynomials. They have a degree of 0. And then x minus 2 is a polynomial. So by definition, this is a rational function. So what is happening then when the denominator is 0? What's going on the graph? Well, we have a special feature of the graph that's actually called a vertical asymptote. So a vertical asymptote happens whenever we reduce the numerator and denominator. Okay, we've already got them in reduced or simplified form, and the denominator equals 0. So the denominator equals 0. There's this thing, I'll describe it in a second, but there's this thing called a vertical asymptote happening. So you guys know what vertical means, because we've dealt with vertical lines before, right? Yeah, straight up and down, right? So the part of this definition, the word vertical, we have an idea of. But asymptote may or may not be something that you're super familiar with. So what in the world is an asymptote? this is a super fluffy kind of definition, but for our purposes it will serve us well. Asymptotes are lines that our graph approaches but does not touch. I didn't think to write it on here, but it would be useful for you to realize that we're going to draw them as dotted or dashed. So when we draw these lines, they're going to be dashed lines or dotted lines. Okay, that's going to indicate to us that we're going to not touch them. So our goal eventually in this section is to be able to draw a rational function. And the reality is that your calculators that we've been using a little bit for polynomials in the last section, they don't really draw rational functions very well. They have a really, really difficult time with this idea of asymptotes, and they like to connect things that don't make sense. And that's a flaw in the fact that your calculator does not think the way that you and I can, all right? So yes, can you confirm the graphs sort of with a calculator? Yes, sort of, but if you're relying on your calculator to be able to graph these, you're probably going to have a lot of inconsistencies that are not going to make any sense from a graphical standpoint from thinking about it as opposed to your calculator's computations. So we're going to take this function, same one I've been dealing with since the very first slide, -5 over x minus 2, and we're going to graph a vertical asymptote. So how do we do that? Well, first we have to find it. So as I abbreviate, I'm always going to abbreviate it VA. And we take the denominator, if it's reduced form, and it is, right? Our numerator and denominator don't simplify. So in reduced form, we set it equal to 0 and we solve. So what does this denominator's x value equal? Yeah, it's 2, right? So over on my graph, if we're taking a look at this, 2 is right here, yeah? And it's going to be a vertical line through 2. So I'm going to draw a vertical line through the value x equal 2 on the number line, on the x-axis number line. So I have the advantage of having dotted lines. You don't, unfortunately. So you're going to draw yours in dotted, but it would look something like this. Dotted, dashed, whatever. It is a line, should have arrows on the end of it. I'm not going to be super persnickety about that, but it is a line, it continues. That's it. That's a vertical asymptote. Okay, so we're going to build on this. This is just the first piece in graphing, but vertical asymptotes are the first piece we're going to graph. There's other types of asymptotes. If I talk about vertical asymptotes, you might be inclined to think there's also something called a what? A horizontal asymptote. That makes sense, right? And there are. They aren't always present, but there are 3 different cases to consider for horizontal asymptotes. Leave some space after each of these. Okay, after line 1, leave you a line or something like that so I can write in some details. But there are 3 possibilities. We could have the degree of the numerator smaller than the degree of the denominator. We could have it bigger than the degree of the denominator. Or they could be equal. Do you remember what degree means when we're talking about polynomials? The largest exponent. Good job, Karen. So we're looking at largest exponents. So, if the degree of the numerator is smaller, and I'll abbreviate horizontal asymptote as HA, my horizontal asymptote is y equals 0. Notice my horizontal asymptote is not 0. 0 is a number. Y equals 0 is a line. Okay? So we're going to write it as a line because that's what it is. It's a line. Degree of the numerator is smaller, we have the horizontal asymptote y equals 0. If the degree of the numerator is bigger, there is no horizontal asymptote. Something else is going to happen in a minute, but it doesn't have one of these. The third case is the one that's the most awkward to write down, but it's really easy to do. So the horizontal asymptote, if the degrees are equal, is y equals the ratio of leading coefficients. So what does that mean? Do you remember what the word leading or the phrase leading coefficients meant for polynomials? Those were transformations that we did. That's not leading coefficients. I think I know where you're coming from though, because those stretches are leading coefficients. Let's take a look at the example I had before and see if we can decide. This equation right here, what is the leading coefficient on the denominator? Somebody said it. It's a 1. Okay, so what are you looking at when you decided it was 1, Keely? Okay, so you looked at the x. X is my degree highest, the highest degree term, right? And the coefficient in front of the x is a 1. Come on. Okay. Now, on this example, the leading coefficient in the numerator is just -5 because it's the only thing in the numerator. Not real exciting. But this is not an example of the third case anyway, because the coefficient or the degrees are not the same. What's the degree of this numerator? You know? I can't hear you. Nope, -5 is the leading coefficient, but it's not the degree. It's 0. Do you know why, Karen? Nope. Does anybody want to have a guess as to why the degree of the numerator is 0? Okay, so why is the degree, what's the degree of the denominator? Let's go to that one next then. Y'all are making me really scared to grade your tests that you took yesterday. If we can't answer the question of what's the degree, we got some problems. What's the degree of the denominator? You guys told me how to find degrees just a minute ago. It's 1. How come, Sarah? Why is the degree of the denominator 1?
Isn't it just like understood?
Okay, where is this 1, this understood, coming from? Okay, what do you mean by on the x? Thank you. Exponents. It's all about exponents. Okay, good. Because there's 2 understood ones here. There's an exponent 1 and there's a coefficient 1, right? I want to make sure we're thinking the right thing. This one right here tells me that this degree is 1 because the exponent is 1. So if the highest exponent in the denominator is a 1, what is the highest exponent in the numerator? You guys have already told me that you think that the degree is 0, which it is. Nope, there is no degree 1 in the numerator. There is no exponent of 1 in the numerator. It's really huge. What is x to the 0? No, it's not 0. It's 1. Anything to the power of 0 is 1. Yeah. So that's why this is degree 0. It's because it's a constant, and constants have a degree of 0. It's x to the 0 power. So this example, which we're about to do here in a minute, is not got the degree on top and the degree on bottom the same. They're actually different. Which one's smaller? The numerator, yes, the degree is smaller on the numerator, which means if I'm looking at these options right here, it's the numerator that's smaller, and I'd be in case 1 on the example that I've been working with, right? Let me show you real quick about the degree of the denominator, degree of the numerator being equal so you can see what that looks like. if you had a function that said x minus 5 instead over x minus 2, these would both have degree 1, right? Let me make it just a little bit more interesting so that I can talk. If you're looking at these and they both have degree 1, right, it would be an example of the third case. And what you would do is you would take the leading coefficients. So what's the coefficient on the top? It's 2. And what's the coefficient on bottom, leading coefficient? It's a 1. So you'd get a horizontal asymptote of y equals 2. That's how you do it. It's really directly, you know, the numbers are there, and they're usually already even written in a way that looks like they're being divided kind of too. So that's this third case. So we're going to take a look at these different cases as they happen. I meant to go back. Obviously, my slide didn't get in there for this to be a part B here. On part B of the same example we were working with before, what I want to do is I want to graph all horizontal asymptotes. Okay, same problem. We already talked about which case we were even in. What case are we in when we do this? It was case 1, and case 1 says that my horizontal asymptote is what?
0.
Okay, can you say that with a line instead of a number? Good. So it'd be y equals 0. Okay, make sure that you're stating lines when you get to the asymptotes. So where in the world is y equals 0? On the origin. Where else? There you go. It's the x-axis. All along the x-axis, y is 0. So this would be the horizontal asymptote I draw. When the horizontal asymptote is the x-axis, that's the hardest one to draw because you've already got your pencil line there, and if you're trying to draw a pencil dotted line on top of it, it's hard to sometimes see. So if you want to use a different color to do these, that might help. Your call on that, but just make sure that I can see it one way or another. Okay? So this is a case of the first, this is an example of the first case. Case number 1, I've got the degree of the numerator smaller than the degree of the denominator, and here's what happens. So let's do another example then. We're going to find horizontal and vertical asymptotes, and I typically find vertical first. How do I find vertical asymptotes? That's right, Trey. We set the denominator equal to 0, and we solve. So I'll add 3 to the right, so 3x is 3. So what is the equation? X equals 1. And notice it says x equals, not just 1. So I'm going to draw a vertical line, because it's a vertical asymptote, at the x value of 1, which puts me approximately right here. And then what do I do for horizontal asymptote?
Ratio.
Yeah, it's a ratio. This is an example of the third case. The degrees are the same. What is the degree of each of the numerator and the denominator here? 1. Thank you. I don't know if you guys just don't want to talk to me today or if you really don't know what's going on. I'm really confused at this point. So please let me know. Help me out. It is 1. The degree on top and the degree on bottom are both 1. So Megan mentioned we were going to do a ratio of the coefficients. It's y equals, what's the leading coefficient on top? 6. And on bottom? 3. And if I simplify that, I get y equals 2. So we're going to draw a horizontal line now at y equal to 2. Shift it up just a touch. Approximately here. And we're done. Some of your homework questions are going to be just like this. They're just going to say, draw on the vertical and horizontal asymptotes. Okay? They're not asking you to graph anything else, just this far. About a third of the homework, I think, does that. All right. So we've done an example of case 1 and an example of case 3. So what do you think I'm about to show you? Case 2. So case 2 is a little weird. this is our example I'm going to get to in a second. But case 2 won't have a horizontal asymptote. So when that happens, oftentimes we instead have a third type of asymptote called a slant asymptote. There is another word for slant asymptote that some books will use. Some books will use the word oblique. So when does this happen? Well, it specifically will happen when the degree of the numerator is exactly 1 more than the degree of the denominator. And we find this by doing long division. Now, long division with functions is very similar to long division with numbers, but I'll bet that it's been a while since you've done long division with numbers. So we'll have to talk through that in a couple of examples. All right, so this says to find all asymptotes, and we start with vertical. Now, the reality is that we have to be a little bit careful. The thing we need to be careful of is we need to be careful that the numerator and the denominator don't have anything that reduce between them, that anything would cancel out, right? This isn't going to be possible on this one for sure. If you notice, there's a 3 at the end, and there's a 2 at the end of this one. So even if the numerator factored, it wouldn't factor into something with a 3. Does that make sense to everyone? Now this numerator specifically doesn't even factor, but even if it did, it would only have 2s and 1s, it wouldn't have a 3. So we do need to make sure, whoops, didn't mean to do that, sorry. Make sure that we're looking to make sure it doesn't reduce. If it doesn't reduce, then we're set to do the vertical asymptote by letting the denominator equal 0. So this is x minus 3 equals 0. So what is my vertical asymptote? Right, x equals 3. And we can go ahead and graph that. So x equals 3 would be right here. Try it again. I'm not drawing well today. Let me try again. All right, we'll do that. All right, so take a look at this one. This is a case number 2 example, right? What's the degree on top? The degree is 2. What's the degree on bottom? 1. Remember, degree is looking at exponents, yeah. So the degree on top is definitely bigger, but it's exactly 1 bigger, right? So since it's exactly 1 bigger, we will have, so I'm going to say we don't have a horizontal asymptote, that was case 2, but we will have a slant asymptote. And the way we find slant asymptotes is with long division. So what in the world does long division look like? Well, think about with me if you had something like 40 divided by 3. Well, you'd put the 40 underneath the division sign and the 3 on the outside, right? So we're going to do the same thing here. The negative x squared plus 4x plus 2 will go under the division sign with the x minus 3 on the outside. So everybody good so far with the setup? And if you can't get the setup, you're not going to be able to finish, so I want to make sure we're good. Okay, now think about this 40 divided by 3 business over here. The kind of questions you might remember asking yourself is something like, how many 3's go into 4? Does that sound right? And the answer here would be 1. And then you would multiply 1 times 3 is 3. So far, so good. Okay, we're going to do the same thing over here on our polynomial. The question's going to sound a little bit different. What we're going to ask ourselves is, what do we need to multiply x by to get negative x squared? That's the same question as how many x's go in. It just sounds funny to say it with variables. So what would I need to multiply x by to get negative x squared? Yep, negative x. And then over here with my values here, once I did get the 1 up here, I multiplied, right? 1 times 3. So we're going to do the same thing over here. We're going to multiply negative x times x, which gives me negative x squared. But I also have to multiply it by the negative 3 part. So what's negative x times negative 3? Positive 3x. It's positive, right? Okay, is that all right? Okay, so come back over then to our example with the 40 and the 3. What did I do after I wrote down the 3 underneath the 4? You subtract, right? Yeah. So that's what we're going to do on ours too. We're going to subtract, but subtraction means changing the sign. So if it's positive, now it's negative, and if it's negative, now it's positive. So I have negative x squared, and I have positive x squared underneath, and those would add to what? 0, which is kind of the whole point that we did that with the division, right? Was because they would become 0. So these add to 0. That's not a good color. How about that one? These add to 0. And then I've got 4x on top of now a negative 3x. So what do those add to? X, yeah, or 1x, yeah. And over here, when I did that, I'd do 4 minus 3 is 1. And then what would I do after I wrote down my 1 as my subtraction with my 40 and my 3? I would bring down the 0, right? Maybe you drew an arrow, maybe you didn't. But the same thing happens in our problem. We're going to bring down the plus 2. Okay, back to our old-fashioned division problem. What did I do next now that I have a 10 down here? Right, I just did it again. I looked at the 3 and I looked at the 10 and I asked myself the same question. How many times will 3 go into 10? Of course, that answer would be 3. 3 times 3 would be 9. And we'd subtract. So over here, what do I need to multiply the x by to get x? 1. Yeah, not very exciting, but that's right. So we're going to have plus 1 up here because it's a positive 1 we're multiplying by. 1's fabulous because multiplying by 1's so nice. 1 times x is x. 1 times negative 3 is negative 3. And then over here with my 10 and my 9, what did I do with the 10 and the 9 next? I subtracted to get 1. So here I'm going to subtract, but subtraction means doing what? Changing the signs. So negatives become positive and positives become negative. That happens to give me then that x and x here add to 0. And at the end I get a 5. Now the reality is, for the purposes of what we're doing, I don't really care what I get at the end. But I know I'm at the end because I have a constant. And I'm trying to divide by something with x in it. So where is my answer? What in the world did I, end up with? Well, up here at the top, that was supposed to be a highlighter. Let's try again. Up here at the top, right here. That worked. That's my equation. Well, at least it's the expression. The equation is y equals the negative x plus 1. That's my slant asymptote. And it is a line, and it is going to be a diagonal line. Slanted, right? It's my slant asymptote. So I've got to plot it just like I would any other line, when we were first working with this back in September. I've got a y-intercept of 1. And I've got a slope of negative 1, which would mean down 1 and right 1, like this. And I'm going to connect those 2 points with a dotted, slanted line. So look something like that. That's a slant asymptote. Okay, so we've explored all the possible asymptotes now. The question is, once I have my asymptotes, what do I do then to get the graph? Because remember, asymptotes are supposed to be things we don't touch, but the graph should be the values we do have, right? It's kind of like the opposite question. Well, the asymptotes actually allow us the spaces where we can find the rest of the graph. They divide my space of my graph into, in this case, all of them that we've done so far, into 4 regions, right? So like on this picture right here, there's a region here, there's a region here, there's a region here, and there's a region here. And the question is, where's the graph? Is it in all those regions? Is it in some of those regions? Is it none of those regions? How do I figure those pieces out? So we're going to do the same kinds of things at the beginning, but we're going to go one step further on the rest of our equations for today. These are asking us now to actually graph the function. Not just find the asymptotes, but graph it. Now the kicker is I still got to find the asymptotes. So I start the process much like I did before. Vertical asymptote. What is the vertical asymptote for this equation? Okay, try again for me on how you said it, Megan.
Y equals 3.
Okay, it'll be x equals, but yeah. Okay, so we've got to set the denominator equal to 0. And when I solve it, I end up with x equals 3. Everybody good with that? And as we do this, I find it easiest to do the graph as I go. I found the asymptote x equal 3, so I'm going to put it on there. X equal 3. What's the next type of asymptote that I would look for? The horizontal asymptote. Which case am I in? The first one, right? My degree on top is 0, degree on bottom is 1. So what's my horizontal asymptote? Y equals 0. And I'm going to plot it. And we've seen a y equals 0 one before. We've talked about the fact that that's the x-axis. So now I've got a graph like this. Okay, so what do I do next? Well, it's actually much like what we did when we looked at inequalities. The last section that we did, we talked about finding these sort of places where it broke my graph apart, right? And we found them by letting things equal to 0 even. And then I chose test points in intervals. Do you guys remember that? Shake your head if you do. We chose numbers to test. Well, we're going to do the same thing here. We need to check numbers. In this case, this horizontal or this vertical line is splitting my graph into 2 pieces, the left piece and the right piece. And I need to test a number on the left and I need to test a number on the right. But I'm not just testing for positives or negatives. I actually need a number this time. So, what values should you test? Well, it's up to you. X equals 0 is always a nice thing to test. I kind of like x equals 0. Numbers that are also nice are numbers that end up giving you a denominator that would equal to 1, because dividing by 1 is also nice. So I tend to do the dividing by 1 bit. So if I choose numbers that are just really close to 3 but on either side, right, here's my 3. So I like to choose the 4 and the 2 because they're 1 in either direction and I get 1s or negative 1s on bottom. Does that make sense? Dividing by 1 and negative 1's a pretty simple division step, and I don't end up with weird fractions when I do that. So I'm going to test points. So this is my test point step of x equals 2 and x equal to 4. If you choose other points, that is totally fine. Not a problem at all. And you're going to plug it in. So our equation said f of x, so this will now be f of 2 equals, I have negative 6 on top, and I have 2 minus 3 on bottom. So what is 2 minus 3? Negative 1. And what is negative 6 divided by negative 1? 6. So I have found an ordered pair, 2 for x, 6 for y. And I'm going to plot it. 2, 6. 2, 6 would be right here. If you chose x equal to 0, let's see, you would actually get 0, 2, and you'd plot that. Totally fine. No matter what you choose, it'll be okay. And then the last one that we're going to test, and it is the only thing we have to test. I'll show you how you connect things, but the other thing to test is x equal to 4. So at x equal to 4, I'm just trying to move that thing. There we go. We're going to test f of 4. So I've still got the same negative 6 on top, and now I have 4 minus 3 on bottom. So what's 4 minus 3? 1. And 6 divided by 1 would be 6. Sorry, I got a negative. I missed it there. Negative 6. Thank you. Okay. I got another ordered pair. My ordered pair is 4, negative 6. So I can plot 4, negative 6, and it'll be right here. Here's the beauty of this. Once you have 1 point, all it takes is 1 point on either side of the asymptote, and you can draw the rest of it. Because you have asymptotes. Asymptotes tell you these are lines you get really close to and don't touch. And there's only one way to do that. So let's start with the first point we plotted. If I'm moving to the left, it has to decrease down to the dotted line on bottom. And if I move to the right, it has to increase to the vertical line on the right. There's no other way to get close to those two lines except for that one right there. And my dot on the left, if I'm moving from the dot on the left to the left, I have to get really close to the dotted line that's vertical. And if I'm moving to the right, I get really close to the dotted line that's horizontal. And it always has those shapes. 1 point. That's kind of a cool thing, because every other time we've had to plot quite a few points, like minimum of 3, right? I guess when we did x squared, or the square root of x, we did 2. But on this one, we only need 1 point to plot a specific portion of the graph. All right, so let's try another one. F of x equals 2x plus 3 over x plus 3. Where do we start when we're graphing? Always, always. Vertical asymptote. You guys are paying attention? That's awesome. How do I find a vertical asymptote? I set the denominator equal to 0. So what is my vertical asymptote? X equals, oh, yep, negative 3. Sorry, I had a plus there. Okay, so I'm going to graph it as I go. X equal negative 3 would put me, whoops, here. After I do my vertical asymptote, what do? Horizontal asymptote. At least I test for it, right? Which case am I in for this horizontal asymptote? This is case number 3. The degrees are the same. So it'll be y equals, and how do I get my horizontal asymptote values then? The leading coefficients, which is 2 and 1. So this is y equals 2. So I'm going to draw a horizontal line at y equal to 2. Good job, guys. Very well done. If I have a horizontal asymptote, I don't test for slants. It's not going to happen, okay? The only time I test for slants is when I don't have horizontals. So I've got all my asymptotes. Now I need to test different portions of my graph. And the dividing value is right here, the vertical asymptote, negative 3. So again, visually speaking, I look at the two numbers on either side of that vertical asymptote. So my preference is I'm going to pick x equal negative 4 and x equal negative 2. You don't have to pick those, but you do have to pick one on the left of it and one on the right of it. So I'm going to test points. At x equals negative 4 and x equals negative 2. And as I do that, I'm going to plug them back into the function. I want to know the y value. So I want to know what is f of negative 4, and in a moment, what is f of negative 2. Now, this one's, got more x's to plug into, so it takes a little bit more work. I have 2 times negative 4 plus 3 over negative 4 plus 3. So, what in the world does that numerator simplify to? All the math there. Negative 5 on top. And my denominator is negative 1. And negative 5 divided by negative 1 would be 5. So this is the ordered pair, negative 4, 5. So I'm going to plot negative 4, 5, which is right here. On the next one, I'm going to plug in negative 2. So 2 times negative 2 minus 3 over negative 2 plus 3. What do I get on top? What is it? I don't think it's negative 1. I think it's negative 7. Is it negative 7 on top? Did I leave something off?
I think the
3 is a positive at the end. Okay. I was like, something feels like it's a little bit off. Yep, that's what it was. Good, we fixed it. So now I do get negative 1. Thank you. Right? Negative 4 and positive 3. What do I have on bottom? I have 1. And negative 1 divided by 1 would be negative 1. So my ordered pair here is negative 2, negative 1. So I will plot negative 2, negative 1. All right, I would like for you to attempt to draw in the curves, and then I'll sketch mine and we'll make sure that they match. So what should the curves look like based on the last problem that we did together? Yeah, so they look something like this on the left and this on the right on this one. You got to go through the dots you plotted. I think that you guys got that, but I probably shouldn't say it out loud. Okay? Okay, let's try another one. The next one's a bit more interesting. Can you tell maybe why it might be more interesting? There's factoring that we're going to have to do in this problem. And we have to do it somewhere along the way. Starting with the factoring is going to make it easier because the first thing we're going to actually find is the vertical asymptote, right? So we're going to need it factored at some point anyway. So let's go ahead and factor at the beginning. Numerator. Pull out an x, which leaves me with x minus 10. I can't do that in the denominator, but I can write it as two binomials. Good job. X minus 7 and x minus 3. It's important to pause here and make a note to ourselves. There's no reducing, right? No reducing here. If there were, we'd mark lines through them and then we'd keep going with the reduced form. Are you with me? Okay, so this one can't be reduced, but we needed this actually for our next step anyway, where we find vertical asymptotes. How do we find vertical asymptotes? Set the denominator to 0, and my denominator in factored form, because that's most helpful, looks like this. We've done this before. We've set things like this equal to 0 before. What do we do next? We don't want to distribute. That would be unhelpful. Set was that? Yeah, set each one individually equal to 0. That will be helpful in this case. Like that. So, what do I get? X equals 7 and X equals 3. So what do you think that means is going to happen on my graph? I have 2 vertical lines. That's exactly right. Good job. So I need to draw in 2 vertical asymptotes on this one, which is exactly why this becomes a little bit more interesting. My goodness. I feel like I should put some glasses on. That might help me out here. Okay. 2 vertical asymptotes. After I find vertical asymptotes, what do? Horizontal asymptotes. Which case are we in? Third case. And honestly, I know I've got it in factored form, but for looking at horizontal asymptotes, the original form it was given is easier to look at. They're both the same degree, right? Yeah. So I'm in case 3. So it's y equals what? Yeah, it's 1 over 1 because the leading coefficients are both 1. Or you can simply write that this is y equal 1. And I have a horizontal asymptote at y equal 1. Okay. How many regions do we have on this graph? Okay. How many different... You're right that we have 6. If I don't consider top versus bottom, then that means I would have 3, right? So there's 3 different portions. There's a portion that's sort of said on the left. There's a portion that's on the right, and there's a portion that's trapped in the middle. Are you guys with me? So your absolute minimum number of test points would actually be 3. But that middle section can do a couple of different things, so we actually need to test 2 points in the middle section. There are going to be 4 test points. So, here's my test points. Again, what I would recommend to do is to do 1 over here to the left of the 3. So I would test 2 because the division ends up being easier, usually. I would test 1 point that's on the right-hand side of your farmost right value, which I would test 8. And then I need to test 2 points in the middle. And they kind of need to be specific. I need to make sure of what's happening as I get close to the asymptotes on the right and on the left, on both pieces. So I'm going to test, again, 1 to the right and 1 to the left of each of the asymptotes. So I'm going to test 4 and 6 as well. So we'll test x equals 4 and x equals 6. If you have a calculator, I'd recommend you grab it out because these are not as clean as the last ones. If I test f of 2, I would have 2 squared minus 10 times 2 over 2 squared minus 10 times 2 plus 21. Or if you want to plug it into the factored form, you could do that. Totally would be fine. But I need to know what happens when I plug in 2. Did you get 0? Okay. Did anybody else get 0 when you plugged in 2? That doesn't sound right. Or did you maybe you plugged in 0. Did you plug in 0, Sarah? Because if you plug in 0, you'll get 0 on it. Okay. What do we get on top? Let's try that. Let's do it a piece at a time. What is 2 squared minus 10 times 2? Negative 16, that sounds right. What do you get on bottom? What is it? 5? Ooh, so this is the ugly one. Okay, if I divide that, it's going to be a decimal, but it's not too terrible. What is it? Negative 3.2. Okay, so we ended up with a decimal on this one. Okay, so my ordered pair is 2 and negative 3.2. So I'm at x equals 2, and I'm at negative, was it negative? Yeah, negative 3.2. So I'm somewhere right here. Okay, just need to plot it right. All right, let's try it with 8. F of 8. So I have 8 squared minus 10 times 8. over 8 squared minus 10 times 8 plus 21. What do I get on top? Negative 16? Really? Like again? Wow, okay. And then 8 squared minus 10 times 8 plus 21. Do I get a 5 again? Fantastic. Well, the good news is we know what that decimal is, right? Let's see here. All right, so this is negative 3.2. This ordered pair would be 8, negative 3.2. So I've got sort of a mirroring effect going on over here. That good? All right, let's see what happens then at 4 and 6. F of 4. So I'd have 4 squared minus 10 times 4 over 4 squared minus 10 times 4 plus 21. What is my numerator? Negative 24. And my denominator? What was it? Negative 3. Oh, that's a nice value. What's negative 24 divided by negative 3? It's 8. So my ordered pair on this one is 4, 8. So on my graph, I'm here. And let's try the 6. F of 6 is 6 squared minus 10 times 6 over 6 squared minus 10 times 6 plus 21. What do you have on top? Negative 24. Do we get negative 3 on bottom again, or is it something different? Okay. Now, it will not always be symmetric like that, and that's actually why I needed you to test both points. So, I think you know what to do on the far left and the far right. If you were to connect these, it would look like this. Everybody's good with that, yeah? That's like what we've done before. Although it's interesting, they're both below the axis now, right? Instead of being one on top and one on bottom. In the middle, literally you can have one of 3 things happen when you have a graph like this. This case actually has a graph that's doing this. It kind of looks like a parabola in between. Okay? And the parabola can either be above the axis or below. So obviously that's 2 different possibilities. A third possibility, and of course this is not what's happening here, but let me show you what it could have looked like. It honestly could have looked like this. Now, you should be a little concerned. Because what did it cross? It crossed an asymptote, right? The horizontal asymptote. So, I gotta be honest and go back and tell you that a horizontal asymptote could be crossed in the middle of the graph, but not on the ends. Asymptotes are really lines you don't cross as the values get really big on the ends of the graph. So it really kind of could cross in the middle. Like, that's a possibility. So I kind of lied just a little bit. It's not exactly what I wrote down before, but most of the time it works. So on this one, it didn't look like that. It looked like this. Okay? All right, have just a couple more things to graph with you. One I want to show you is I want to show you what happens when you have a slant asymptote, because honestly, they look a little weird. Okay? So let's do a slant asymptote. This one, vertical asymptote to start, of course. Apparently my denominator is having x plus 3s and x minus 3s was just a super popular thing as I was doing this lesson. I don't know why, but every example that the book kept throwing out with me had it, and I was like, okay, fine, whatever. So if I look at this one, I set the denominator equal to 0. I get a vertical asymptote at x equal negative 3. And what can you tell me about horizontal asymptotes on this one? Okay, I think you're talking about or thinking about degrees. Let's go back for just a second. Which case am I in for the horizontal asymptote? Case 2. The degree on top's bigger, right? And I think that's what you're meaning, Keely, is that it's exactly 1 bigger. Yeah, and it is. So what it means first, before I get to that point, is that there isn't a horizontal asymptote because the degree on top is bigger. But because it's exactly one bigger, as you noted, we will have a slant asymptote. Okay? So slant asymptotes we do division with, which I could tell you guys are really excited when we did it before, so we should probably try another one again. We divide the top by the bottom. The top was x squared plus 5x plus 5. And divide by the bottom, which is x plus 3. Okay. What do I have to multiply x by to get x squared? X. So I'm going to write an x up here, and I'm going to multiply. X times x is x. X times 3, sorry, x squared. And then x times 3 is 3x. After I multiply, what do? I subtract, and subtract means I change the signs. I have the advantage of having a color with me. It might be helpful if you want to change your signs to do the same, your call. That will always result in these adding to 0. That's the whole point. And then in the middle, I have 5x minus 3x, which is 2x plus 5. Plus 5 is going to come down. And I ask the same thing. What do I have to multiply x by to get 2x? I have to multiply by 2. So that gives me 2x. And then 2 times 3 is 6. And I change my signs. This adds to 0. Again, that's the point. And on the right, I have positive 5, negative 6, so it's negative 1. Although, let's be honest, it doesn't really matter. The part that does matter is what came out on the top, the quotient, the x plus 2 part. So my slant asymptote is y equals x plus 2. That's not a horizontal line or a vertical line. It's a slanted line, right? A diagonal line with an a y-intercept of 2. So I'm going to plot 2 and a slope of 1. So we would go up 1 and right 1. And I'm going to connect these two with a dotted line. That's my slant asymptote. Vertically speaking, I've still split the graph into two pieces, the left piece and the right piece. Do you guys see that okay? So I still only need to test 1 point on the left and 1 point on the right. Only 2 test points. So using those 2 test point ideas, or using that 2 test point ideas, what would you like to test? -4 and, what was it? -2. Those sound good. So I'm going to do f of -4. So that would give me, let's see, -4 squared. So that's the same as +4 squared, just so you know in terms of typing your calculator. -4 squared plus 5 times -4 plus 5 over -4 plus 3. I'll do the denominator. It's -1. What do you get on the numerator? It's also 1? Positive this time? Okay, so what is 1 divided by -1? -1. Very good. So my ordered pair then here is -4, -1. That red's hard to read. Sorry about that. So -4, -1 would be right here. It's slightly above the dotted line. Slightly. And then we'll test the point at -2. So f of -2 would be -2 squared plus 5 times -2 plus 5 over -2 plus 3. Denominator then is 1. What's our numerator? What is it? -9? -1's what I have in my notes. Okay, so I have a couple people saying they got -1, right? Okay. All right, so this ordered pair then would be -2, -1. It doesn't usually end up being the same y value. In fact, when that happened on my notes, I double checked mine because I thought, well, that's sort of weird. Doesn't usually happen that way. But it is here, actually the same y value. So we have our ordered pair -2, -1. The difference here is that -2, -1 over here is actually slightly below the dotted line because the dotted line slants, right? Do you guys see that? So what does this look like? Well, I've got to get close to the dotted line as I move to the left. So it's got to sort of come down at an angle to this dotted line, right? So it looks like this. And it's got to get, as I go to the right, it's got to get close to the vertical line because it's trapped. So I'm going to go up to the vertical line here. Okay, so it's at an angle. And the same thing is going to happen over here. If I go to the left, I get close to the vertical line, and if I go to the right, I get close to the slant line right here. So it really looks like we took the graph and we slanted almost the whole graph, or we, sort of stretched it out of shape. One last example, and then we're going to call it quits today. Are you ready? All right, so just like we did transformations before with x squared graphs and x cubed or x square root of x graphs and absolute value graphs, we can do them with these graphs as well. So if I'm given a graph to start with, this is the graph of 1 over x squared. Okay, they're actually going to start with a graph that they give you. And they want you to translate it. Transform it, move it around, stretch it out of shape, shift it left, right, flip it over, whatever they're asking you to do. On this one, they have a 2 right here and a 4 right here that have changed things. You guys see that? All right then. What in the world does that 2 do based on previous work we've done? Good, it moves it left 2. And what will the 4 do? It will move it up 4. Now here's the cool thing. Do you see the dotted lines drawn on this graph? They're a little bit hard to see from your distance, I think. But do you see them? They happen to be on the x and the y axis. So the cool thing is that you can take the asymptotes, the dotted lines, and you can shift those first. So my vertical line, if I shift my vertical line and I move it up, it doesn't do anything, right? Vertical line go up and down, it doesn't do anything. But if I shift it left or right, that actually moves it. So my vertical line actually will be the one that gets shifted to the left and it changes it. So here's the left 3. The dotted vertical line that was on the y-axis moved left 3. Oh, I'm sorry, it was left 2. I'm in the habit of doing everything by 3s because we were working with 3s so much. There we go. And then on the dotted line that's the horizontal line, shifting it left and right doesn't move it, right? But if you shift it up or down, it would. And that's supposed to be shifting it up 4. So my horizontal line gets shifted up to here. So I physically took this axis and I shifted it up and left. Do you guys see that? And once I have those pieces, it's easier to draw in the other pieces shifted as well because I know where I'm bounded between. So as I'm drawing the rest of it, I can actually shift it as well. It's here and here, roughly speaking. Are my graphs perfect? Absolutely not. They never will be. But you have the idea, right? Those 2 pieces are now shifted up and left.